The vastness of space stretches beyond the grasp of human imagination, an endless tapestry of stars and voids that humbles even the most curious minds. Our solar system, a familiar haven of planets and moons, feels like a cozy corner of the cosmos, where Earth spins in quiet harmony alongside the fiery reds of Mars and the swirling storms of Jupiter. Yet far beyond the sun's warm embrace, past the invisible boundary of the heliopause some 18 billion kilometers away, lies the enigmatic frontier of interstellar space, a realm of cold, uncharted mystery. Only the Voyager probes, humanity's farthest-reaching emissaries, have crossed this threshold, carrying our hopes into the unknown. Until recently, just 2 objects from that distant abyss had ever ventured into our solar system: the peculiar Oumuamua in 2017 and the comet-like 2019. These cosmic wanderers stirred awe and wonder, hinting at secrets from star systems we may never touch. For years, we waited, our telescopes scanning the heavens, wondering if another visitor would grace our skies. Now a new discovery has reignited that spark of curiosity, pulling our gaze back to the stars with a mixture of excitement and reverence. On July 1st, 2025, a telescope in Chile captured a fleeting glimpse of something extraordinary. A third interstellar object, now known as 3I/ATLAS. This celestial traveler, hurtling toward our sun, promises to unravel new mysteries about the universe and our place within it. Join this journey as we explore everything known about 3I/ATLAS, a comet that carries the weight of distant worlds and the promise of cosmic revelations, set to make its closest approach to our star before the year's end. This interstellar visitor, first spotted as a faint glimmer against the dense star field of the Milky Way, has already captured the imagination of astronomers worldwide. Initially dubbed A11PL3Z, it was detected by a NASA-funded telescope in Rio Hurtado, Chile, part of the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This network of 4 telescopes, scattered across Chile, Hawaii, and South Africa, tirelessly scans the night sky, capturing hundreds of images each evening to track objects that might threaten Earth. On that fateful July night, the Chilean telescope turned its gaze toward the constellation Sagittarius near the galactic plane, a region so dense with stars that many surveys avoid it, fearing their senses will be overwhelmed by the brilliance. Yet Atlas thrives in such challenging conditions, its wide field lenses designed to pierce the crowded heavens. In 4 30-second exposures, it caught a moving dot, distinct from the static stars, racing toward the inner solar system at an astonishing speed. Within hours, the discovery was reported to the International Astronomical Union's Minor Planets Center, the global authority on cataloguing celestial bodies. The center issued an electronic circular, sparking a frenzy of follow-up observations that revealed a stunning truth. This object was not born in our solar system. Its trajectory, far too fast and unbound by the sun's gravity, marked it as an interstellar interloper, the third of its kind ever observed. The confirmation of 3I/ATLAS as an interstellar object came swiftly thanks to a global network of telescopes and the sharp eyes of both professional and amateur astronomers. Pre-discovery observations uncovered in archival data extended the timeline of its detection back to June 14, 2025, with contributions from the Zwicky Transient Facility in California and other ATLAS telescopes. These earlier sightings some as faint as a whisper against the galactic backdrop, allowed scientists to map its path with greater precision. The object's orbit was unlike anything in our solar system, a hyperbolic trajectory with an eccentricity of 6.3, far exceeding the threshold of one that defines a bound orbit. For context, a perfectly circular orbit has an eccentricity of 0, while anything above 1 indicates an object free from the gravitational tether of its star. This extreme eccentricity, among the highest ever recorded, suggests 3IATLAS is not just passing through but hurtling through our cosmic neighborhood with a velocity that defies comprehension. 61 kilometers per second, or roughly 137,000 miles per hour. To put that in perspective, it could traverse the distance from Earth to the Moon in just over an hour. Compared to Oumuamua's 26 kilometers per second and Borisov's 32, this speed marks 3IATLAS as the fastest interstellar visitor yet, a cosmic sprinter racing toward the Sun. As astronomers pieced together its trajectory, they realized 3IATLAS was no ordinary space rock. Early images hinted at a faint coma, a glowing halo of gas and dust that forms when a comet's icy surface warms and sublimates under solar radiation. By July 2nd, observations from telescopes in Chile, Arizona, and Hawaii confirmed this cometary activity, revealing a short tail stretching just 3 arcseconds across the sky, about 25,000 kilometers in length. This led to the object's dual designation, 3I/ATLAS for its interstellar origin, and C 2025 N1 for its cometary nature. Unlike Oumuamua, which perplexed scientists with its lack of a visible coma or tail, 3I/ATLAS aligns more closely with 2I/Borisov, a textbook comet with a prominent coma and tail. Yet its activity is subtler, its coma less expansive than Borisov's, which grew by 1% daily and boasted a tail spanning 140,000 kilometers. This muted activity suggests 3I/ATLAS may not yet be close enough to the Sun for its water ice to fully sublimate, or it may have a different composition, one that holds its secrets more tightly. As it approaches its perihelion on October 30th, 2025, at 1.4 astronomical units just inside Mars orbit, it may awaken, its icy nucleus erupting into a brighter coma and a more pronounced tail, offering a clearer glimpse of its true nature. The size of 3I/ATLAS sets it apart from its predecessors, adding to its allure. Estimates based on its brightness and assumed albedo, a measure of how much light it reflects, suggest its nucleus could be as large as 7 to 15 miles across, dwarfing Oumuamua's mere 200 meters and Borisov's 1-kilometer diameter. If these estimates hold, 3I/ATLAS is the largest interstellar object ever observed, a behemoth by cosmic standards. Its brightness, currently hovering between magnitudes 17.7 and 18 in the Atlas O band, is remarkable for an object so distant at 4.5 astronomical units when discovered. This brilliance, coupled with its size, makes it a prime target for study, as it reflects more sunlight than the dimmer Oumuamua or even Borisov. Yet its coma complicates efforts to measure its solid core, as the surrounding dust scatters light, obscuring the nucleus. Observations from the Vera C. Rubin Observatory, which serendipitously captured 3I/ATLAS during its initial tests, suggest a nucleus closer to 7 miles wide, a figure that could refine as more data pours in. This observatory, with its massive digital camera, promises to revolutionize the hunt for interstellar objects, potentially spotting dozens more in the coming decade. For now, 3IATLAS stands as a testament to the power of modern telescopes, its discovery a preview of the cosmic discoveries awaiting us. The trajectory of 3IATLAS offers clues to its origins, painting a picture of a traveler from a distant corner of the galaxy. Unlike Oumuamua and Borisov, which approach the Sun head-on relative to its motion through the Milky Way, 3IATLAS arrives side-on, perpendicular to the Sun's path, from the direction of the galactic center. Its retrograde orbit, inclined at 175 degrees to Earth's orbital plane, suggests it hails from the Milky Way's thick disk, a region of ancient stars that formed billions of years ago. Models like the Oumuamua-Oxford model, applied shortly after its discovery, estimate 3I/ATLAS could be 7 to 11 billion years old, far older than our 4.5 billion-year-old solar system. This staggering age implies it formed in a star system that predates our own, perhaps around a red dwarf or a star long since burned out. Its high velocity supports this hypothesis, as objects in the galaxy tend to accelerate over time, stirred by gravitational interactions with stars and clouds. If true, 3I/ATLAS is a relic of the early universe, carrying materials forged in environments alien to our own, a time capsule from a cosmos that no longer exists. The composition of 3I/ATLAS offers further hints about its distant origins. Multiband observations reveal a reddish hue, similar to Borisov and D-type asteroids in our outer asteroid belt, suggesting a surface rich in organic compounds or dust. Its coma, though faint, contains water ice and dust, confirmed by telescopes like the European Southern Observatory's Very Large Telescope. Unlike Borisov, which had a high abundance of carbon monoxide, 3I/ATLAS's chemical makeup remains less clear, as its distance and modest activity limit spectroscopic data. As it nears the Sun, warming its surface, astronomers hope to detect gases like carbon dioxide or ammonia, which could reveal whether it formed in a carbon-rich or water-rich environment. Such data could pinpoint its birthplace, perhaps a star system with conditions vastly different from our own, where ice is condensed in unique ways. The James Webb Space Telescope, with its unparalleled sensitivity, may soon provide spectra to unlock these secrets, offering a glimpse into the chemistry of a world beyond our reach. The discovery of 3I/ATLAS has reignited questions about the frequency of interstellar visitors. Early estimates based on Oumuamua and Borisov suggested a density of 0.1 to 1 interstellar objects per cubic astronomical unit. However, Atlas's 3-year search, yielding only 3I over Atlas, points to a sparser population, perhaps 0.001 per cubic astronomical unit. This low density underscores how rare these encounters are, yet it also highlights the limitations of current surveys. Smaller objects, dimmer than 3I/ATLAS, may slip through undetected, or the galactic center's dense star field may hide others. The Vera C. Rubin Observatory, set to begin its legacy survey of space and time, could change this, potentially spotting up to 50 interstellar objects over the next decade. Each discovery adds to our catalogue, refining our understanding of how many such wanderers drift through the galaxy and how they form. For now, 3I/ATLAS reminds us that the universe is vast, and our glimpses of its travelers are fleeting but profound. The behavior of 3I/ATLAS as it approaches the Sun holds the key to its mysteries. Its current brightness and faint coma suggest it is just beginning to awaken, its ices responding to the Sun's distant warmth. As it crosses the asteroid belt and nears Mars's orbit, solar heating may intensify its activity, producing a larger coma and a more visible tail. Observations from the Lowell Discovery Telescope, optimized for low-horizon viewing, will track it closer to perihelion than most ground-based facilities. Even Mars-based spacecraft, like NASA's Marvin Orbiter, could capture images as 3I/ATLAS passes within 19 million miles of the Red Planet in October. However, there's a chance it may not survive its solar encounter. Borisov fragmented after its perihelion, its nucleus splitting under thermal stress, while Oumuamua endured despite its lack of ice. The fate of 3I/ATLAS, whether it holds together or breaks apart, will reveal the strength of its nucleus and the volatility of its ices, offering clues about its formation and journey. The possibility of visiting 3I/ATLAS with a spacecraft, though tantalizing, remains out of reach. Studies suggest a probe launched from Earth would require an impractical velocity change of 7 kilometers per second to intercept it. A launch from Mars, however, could reduce this to 5 kilometers per second, feasible for a flyby in October 2025. The European Space Agency's Comet interceptor mission, set to launch in 2029, is designed to chase such transient visitors. But 3I/ATLAS's trajectory makes it an unlikely target. Instead, astronomers rely on remote observations with telescopes like the Hubble and James Webb, poised to capture detailed images and spectra. These instruments could detect non-gravitational acceleration, as seen in Oumuamua, which hinted at outgassing invisible to most telescopes. Such a discovery in 31/ATLAS could confirm whether it shares this enigmatic trait, further distinguishing it from Borisov's classic cometary behavior. The philosophical implications of 3I/ATLAS stretch beyond its physical properties, touching the core of our cosmic curiosity. Each interstellar object is a messenger from another star system, carrying the story of its birth in a place we cannot visit. Unlike the planets and asteroids of our solar system, which share a common origin, 3I/ATLAS is a true outsider, formed in an alien environment billions of years ago. Its presence challenges us to consider the diversity of worlds beyond our own, systems where stars burn, cooler or brighter, where ices and minerals form under conditions we can only imagine. By studying its composition, trajectory, and behavior, we glimpse the processes that shape planetary systems across the galaxy. Are comets like 3I/ATLAS common in other systems, or is its size and age an anomaly? Does its reddish dust hint at organic molecules, the building blocks of life, forged in a distant nursery? These questions drive astronomers to keep watching, to keep probing, knowing each answer brings us closer to understanding our place in the cosmos. The public's fascination with 3I/ATLAS mirrors the scientific excitement amplified by the global reach of modern astronomy. Amateur astronomers, armed with modest telescopes, contribute observations alongside professionals, posting findings on platforms like the Astronomer Telegram. Images shared by observers like Philip Romanov, who captured 3I/ATLAS on July 2nd, show its faint glow against a starry backdrop, a testament to the collaborative spirit of discovery. For those without telescopes Online tools like NASA's JPL Horizons allow anyone to track its position, offering a personal connection to this cosmic visitor. From now through September, 3I/ATLAS will be visible in the evening sky, a dim speck requiring long exposure photography to capture. After its perihelion, it will reappear in the morning sky by December, near the star Zawijava in Virgo, potentially brightening as it reflects more sunlight. These opportunities to witness 3I/ATLAS, whether through a lens or a screen, invite everyone to share in the wonder of a universe that sends us such rare and fleeting gifts. The differences between 3I/ATLAS and its predecessors highlight the diversity of interstellar objects, each a unique puzzle piece in the galactic story. Oumuamua, with its elongated shape and mysterious acceleration, defied easy classification, sparking theories from primordial fragments to alien artifacts, though the latter has been largely debunked. Borisov, by contrast, was a classic comet, its carbon monoxide-rich coma suggesting a formation in a cold, distant system. 3I/ATLAS, with its massive size and ancient origins, adds a new dimension to this narrative. Its modest activity, compared to Borisov's vigorous outgassing, suggests a nucleus that may be less volatile or more tightly bound. Yet its reddish color and water-ice coma align it closer to Borisov than Oumuamua, hinting at a shared heritage among comets from other stars. These comparisons fuel speculation about the environments that birthed them. Were they ejected by gravitational disruptions, or did they wander freely after their parent stars died? Each object refines our models, narrowing the possibilities and sharpening our questions. The timing of 3I/ATLAS's arrival is serendipitous, coinciding with the dawn of a new era in astronomy. The Vera C. Rubin Observatory, with its first images released in June 2025, has already demonstrated its power by capturing 3I/ATLAS before its official discovery. Its 10-year survey will likely uncover many more interstellar objects, transforming rare encounters into a steady stream of data. This shift could redefine our understanding of the galaxy's population of rogue objects, revealing whether 3I/ATLAS's size and age are typical or exceptional. Meanwhile, telescopes like the James Webb and Hubble, with their ability to probe faint and distant targets, stand ready to dissect 3I/ATLAS's light, searching for chemical signatures that could link it to specific stellar environments. The data collected in the coming months, before it fades from view in September and reappears in December, will shape our theories about planetary formation, interstellar travel, and the potential for life elsewhere in the galaxy. As 3I/ATLAS streaks toward its solar rendezvous, it carries more than just ice and dust. It bears the weight of our curiosity, our longing to connect with the broader universe. Its journey, spanning billions of years and countless light years, reminds us of our own fleeting presence in the cosmic story. We are but a moment in the life of this ancient comet, yet we have the privilege of witnessing its passage, of capturing its light and unraveling its secrets. By December, when it emerges from the sun's glare, it may shine brighter, its coma and tail a beacon in the morning sky, or it may fade, its nucleus fracturing under the sun's heat, leaving only fragments to drift back into the void. Either way, 3I/ATLAS will leave its mark, not just in our data, but in our imagination. A reminder that the universe is alive with travelers, each carrying a piece of the infinite. So take a moment to look up, to track its path online, or to dream of the worlds it has seen. What stories does it hold, and what will we learn from this plucky interstellar visitor before it vanishes forever?